Bismillahirrahmanirrahim. Assalamu alaikum. My name is Najaf and my roll number is 21TE06. Today I will be discussing lab number 5 of digital signal processing, and the lab title is Representation of Discrete Time Digital Signals into Frequency Domain. The lab objectives are representation of discrete time digital signals into frequency domain, resolution of spectrum, computation of magnitude, phase, and power spectrum, spectrum leaking and avoiding spectrum leaking. DFT calculation. Discrete Fourier transform can be calculated by using the formula given below. An inverse discrete Fourier transform can be calculated by using the following formula given below. The point to be noted here is that n is considered as length of the signal, but it may vary by adding trailing zeros. Task number 1. Make your own functions myDFT, myIDFT for calculating discrete Fourier transform and its inverse using the above given formulas. We have been given 4 signals x1, x2, x3 and x4. Here we make the function myDFT, and myDFT takes an input vector x and returns the discrete Fourier transform of x denoted by x. Here in this line, the length of the input vector x and assigns it to the variable n. This line initializes an output vector capital X of zeros with the same length as the input vector small x. This vector will store the discrete Fourier transform coefficients. Then we used a for loop. This line states a loop over the index k from 1 to n, which represents the frequency index in the discrete Fourier transform. This line starts a loop for the index k, kth element of the output vector x to 0 before calculating its value in discrete Fourier transform. This line starts an inner loop over the index n from 1 to n, which represents the time or sample index in the input signal. This line here computes the discrete Fourier transform coefficient x of k by summing up the product of each sample x of n in the input signal multiplied by the complex exponential term exponential of minus 2j pi into k minus 1 multiplied by n minus 1 divided by n. Next, we created a function with the name myIDFT that takes an input vector x and returns the inverse discrete Fourier transform of x denoted by small x. This line determines the length of the input vector capital X and assigns it to the variable n. This line initializes an output vector small x of zeros with the same length as the input vector capital X, and this will store the inverse DFT values. Next, this line starts a loop over the index small n from 1 to capital N, which represents the time or sample index in the output signal. This line here initializes the nth element of the output vector x to zeros before calculating its value in the inverse discrete Fourier transform. Next is the inner loop over the index k from 1 to n, which represents the frequency index in the discrete Fourier transform. This line computes the nth sample of the inverse discrete Fourier transform signal by summing up the product of each DFT coefficient x of k multiplied by the complex exponential term given. Now, moving on to the task. We have four test cases x1, x2, x3, and f4 that are defined as the input signals. The discrete Fourier transform of each input signal is computed using the my-DFT function, resulting in capital X1, X2, X3, and X4. For reconstruction of the original signals, we use the inverse discrete Fourier transform function of each DFT result, and it is computed using the my-IDFT function, which results in x1 reconstructed, x2 reconstructed, x3 reconstructed, and x4 reconstructed. For displaying the discrete Fourier transform results, we use the function display. Likewise, we did for the inverse function. Now, when we will run this code, we will see first we observe the discrete Fourier transform results for each signals x1, x2, x3, and x4. Each have its real and imaginary parts. For inverse discrete Fourier transform results, we see the reconstructed signals x1, x2, x3, and x4, and it has only the real parts. Task number 2. Frequency resolution can be enhanced by adding trailing zeros. Calculate discrete Fourier transform for the following signals and observe the change in the frequency spectrum. Here we have been given 11 signals and we have to observe the discrete Fourier transform of these signals and the change in its frequency spectrum. Here we have several input signals from x1 to x11 of different lengths. Next, we compute the fast Fourier transform for each signal using the inbuilt MATLAB function FFT, resulting in x1, x2 up till x11. For plotting, a figure is created to display the magnitude spectrum of each signal, and subplot is used to arrange the plots in a grid. For each subplot, we used a stem ABS and the signal name to plot the magnitude spectrum of corresponding FFT result X. Here, ABS is used to compute the magnitude of each fast Fourier coefficient. Stem is used to create a stem plot, and the title is used to set the title of each subplot. So when we run this code, here we observe a magnitude spectrum for all the 11 signals. This code essentially visualizes the frequency content of each input signal by plotting its magnitude spectrum. After computing the fast Fourier transform, the magnitude spectrum provides the insight into the distribution of frequencies present in each signal. Number 3 is about the use of MATLAB built-in functions. We have been given arbitrary signals for the calculation of DFT, for extraction of real part of frequency spectrum, extraction of real part of frequency spectrum, extraction of real part of frequency spectrum. The dot must be placed for corresponding divisions, and inverse DFT to time domain representations. Now here we see this line here defines an input signal X consisting of the elements 1, 2, 3, and 4. X is equals to FFT of X is calculates the discrete Fourier transform of the input signal X using the fast Fourier transform algorithm and assigns the value variable x. In the next line, x real is equals to real of x extracts the real part of the frequency spectrum obtained from the discrete Fourier transform and assigns it to the variable x real. Line number 4 extracts the imaginary part of the frequency spectrum obtained from the discrete Fourier transform and assigns it to the variable x imaginary. Line number 5, x magnitude is equals to ABS of x computes the magnitude of the frequency spectrum obtained from the discrete Fourier transform and assigns it to the variable x magnitude. X angle computes the phase angle in degrees of the frequency spectrum obtained from the DFT by taking the arc tangent of the ratio of the imaginary part to the real part. The dot operator is used for element-wise division. The next line, xs is equals to IFFT of x, is used to compute the inverse discrete Fourier transform of the frequency spectrum x, which effectively converts the frequency domain representation back into the time domain representation and assigns the result to the variable x of s. So when we will run this code, we observe that the input line of x has been transformed into the frequency domain using the FFT. By using x real, we obtain the real part of the frequency spectrum. X imaginary gets the imaginary extracts the imaginary part of the frequency spectrum. X magnitude is it computes the magnitude of the frequency spectrum, and x angle computes the angle of the frequency spectrum. Finally, x of s computes the inverse frequency inverse discrete Fourier transform of the frequency spectrum, and it is obtained by the original time domain representation x of s. Task number 4. Calculate DFT and plot magnitude spectrum, phase spectrum, and power spectrum for signals in task number 2 and observe the effect of zero padding. Here we have defined the signals from task number 2 with zero padding at the end to make the length powers of 2 for efficient FFT computation. Then we created a cell array signals to hold all these signals. Then we define titles for each signals. Next we define colors for each spectrum plot in cell array colors. This for loop iterates over each signal, calculates its fast Fourier transform, and plots its magnitude, phase, and power spectra in separate subplots. For each subplot, the x-axis represents the frequency bands, the y-axis represents the magnitude, phase, or power. The stem function is used to plot the spectrum, and different colors are used for each spectrum plot. Now, when we run the code, we observe the magnitude spectrum for x11, which on x-axis we have the frequency bin, and on y-axis we have magnitude. For phase spectrum, we have this plot, and for power spectrum, we have this plot. And we have 11 such figures because we had 11 signals. This is for x10, x9, x8, x7, x6, and so on. That's all from lab number 5. Thank you.